Hello and welcome to today's lesson. In this tutorial, we will find limits as x approaches infinity and determine if sequences are convergent or divergent. So we are in our final topic in pre-calculus, and I've divided it into 3 days. Today is part A, limits at infinity. Let's look at f of x. F of x is x plus 1 divided by 2x. And I have a few questions to ask about this function. First, what is f of 100? Well, x would be the 100, so that's my input. I'm going to input it into this fraction, and I would have 101 in the numerator and 200 in the denominator. If I were to look at the decimal equivalent, that would be 0.505. Great. Let's increase x from 100 to 10,000. If 10,000 goes into our function, then in the numerator I would have 10,001 divided by 20,000. And the decimal equivalent of that would be 0.50005. Okay. A little bit more outrageous, let's make x 1 billion. So I'm going to plug a 1 billion in for x, and 1 billion plus 1 will be 1 billion 1. Thanks for the commas. Plugging in 1 billion into the denominator, 2 times 1 billion would be 2 billion. And the decimal equivalent of this fraction would be 0.500000005. I believe that's correct, 8 zeros. So what's happening as x is getting very large? What is happening to our either fraction or our decimal? Well, hopefully you're seeing that the fraction is trying to become 1/2, or that the decimal is trying to become 0.5. And that's exactly correct. And this is what we're talking about when we're talking about limits at infinity. We're talking about as x gets very, very large. Not even 1 billion. Yes, that's a large number, but think about how about 49 trillion squared? We're talking about very large numbers. And if we're inputting very large numbers into this function, adding 1 is really not doing that much. It's really inconsequential. So you can almost forget about this plus 1 and think of this function as x divided by 2x, which would be 1/2. And if we are talking about very large numbers, the limit as x approaches infinity would be 1/2. It's never going to actually get there. It's never going to be exactly 0.5 because there is ultimately this plus 1, but it's trying to be 0.5, or rather 1/2. And that's what this limit is. I wonder what happens on the other side of the x-axis. What about the limit as x approaches negative infinity? So not very large numbers, very small numbers, negative numbers. If I plug a negative, very small negative number into the numerator, I'll have a negative divided by a negative. And negative divided by negative is still positive, and we would still be at 1/2. So today we'll be plugging in very large numbers for x and seeing what our function will do. Let's look at our next function, g of x. G of x is 5 divided by x squared. Let's imagine plugging in very large numbers into this denominator. Well, since the denominator is the only thing that has a variable this time, the numerator is not going to change. It's going to remain 5. The denominator with very large numbers is obviously going to get very, very large. As the denominator gets large, the whole fraction, if you divide by a very large number, your fraction is going to get very small. The fraction gets very small. As we divide by larger and larger and larger numbers, our fraction is going to be getting smaller and smaller and smaller, and we will say that the limit as x approaches infinity of this function, because the variable is only in the denominator, is going to be 0. And this is a very important concept to understand. It's right here in this box. When we are taking the limit of a function as the domain is getting infinitely larger, and there is only a variable in the denominator, then your limit will always be approaching 0, or the x-axis. This is because the denominator is getting bigger and bigger, so the actual fraction is getting smaller and smaller on its way to being the number 0. We are going to be using this concept for much of today's lesson. And let's look at our example 1. We've got the limit as x approaches infinity of this quantity 4 minus 2 over x. Well, we can first use the properties of limits that we discovered in another lesson. The limit of this difference, we can separate those two things and talk about their individual limits. So the limit as x approaches infinity of 4 and the limit as x approaches infinity of 2 over x. Because the limit of a difference is the same thing as the difference of the two limits individually. And since we have them as individual limits, we can go ahead and evaluate them. The limit as x approaches infinity of 4, well, really it doesn't matter what x is approaching because 4 is never going to change. That's going to that's just going to be a 4. Of course, we have our minus sign. The limit as x approaches infinity of 2 divided by x, for the reasons in our last example, will be equal to 0, because ultimately the denominator will be very large, and 2 divided by a very large number is trying to be 0. And obviously 4 minus 0 is 4. So that would be our ultimate limit here for example 1. So that's kind of an easier problem. Sometimes the problem is a little bit more tricky like this. So I'm going to show you a nice little method that we use to simplify our expressions so that we can take the limits more easily. What we're going to do is we're going to take all parts. And for example, in this example 2, I see 5 parts, 3 in the numerator and 2 in the denominator. We're going to take all parts and we're going to divide them by the highest power that we see on our variable. And once we do that, you'll see what we can do to take the limits. So I'm looking at all 5 of these parts, and the biggest power that I see is x cubed. So I'm going to take each of those 5 parts. I'm going to rewrite my limit symbol. And I'm going to divide each part by x cubed. So I'm going to take 2x cubed and divide by x cubed. And I'm going to take negative 3x and divide by x cubed. And I'm going to take the 1 and divide by x cubed. I'm going to take the 2 parts in the denominator, 5x cubed, and I'm going to divide by x cubed, and 7x squared, and I'm going to divide by x cubed. So I'm going to take every part and divide by x cubed. Now ultimately this is not changing anything. I've basically multiplied all parts of my fraction by 1 over x cubed. So I have not changed anything. But now let's reduce our stuff and see what happens. We've got the limit as x approaches infinity. And let's see, 2x cubed divided by x cubed, of course, is just 2. 3x divided by x cubed would have 2 x's down in the denominator, so I'm going to have 3 divided by x squared. The third one is not going to do anything. In the denominator, 5x cubed divided by 1x cubed would just be 5. And then 7x squared divided by x cubed. 2 of the x's will cancel away, and I will have 1x remaining in the denominator. So after that simple move, we have these 5 parts. And what we can do now is take the limit individually of all 5 parts. The limit of 2, it will always just be 2. The limit as x approaches infinity of this fraction and this fraction would both be 0. Because these fractions only have denominators with variables. So the denominators are getting very large, so the fractions are getting very small. 5 will remain 5. And the limit as x approaches infinity of 7 divided by x, for the same reason as these two, will be a 0. So obviously what's left is 2/5. So that's a good little process that we can do. We take our more complicated fraction, divide each of our pieces, each of our parts by the highest power, reduce all of those pieces, and then take the limit individually. What I'd like for you to do is try These three problems, very similar problems, you're going to be doing the same exact technique on all three of these. And when you get your final answers, I'd like for you to make a connection with what the function started as. So please pause the video right now, try this method on each of these three problems, and then we'll reconvene and talk about the answers. Pause now. Thank you. All right, thanks for trying those three problems. Here is my work. For try 1, you should have gotten an answer of 0. For try 2, you should have gotten an answer of negative 2/3. And for try 3, your answer was does not exist. Feel free to pause the video and follow my work if for some reason you did not get these three answers. Let's look at try 3. In this case, our highest power was x cubed. And when we divided every piece by x cubed and simplified our parts and then took the limits, we had negative 2 plus 0 divided by 0 plus 0. But you can never divide by 0. Negative 2 divided by 0 is an undefined value. This limit did not exist. Also, make sure that you have this in your work. The limit symbol is in our first two steps. But once we have our pieces in such a way that we can take the limit symbol goes away and we just introduce an equal sign. I didn't work across this time because I knew that I'd run out of room, but the limit symbol is not here. Once you evaluate the limit, there's no limit symbol anymore. We just have the numbers. So did you notice anything interesting with your three answers and the original function that you were dealing with? I think the biggest clue is the second answer, negative 2/3. I see negative 2/3 right here. And that reminds me of our rational functions when we were graphing. Do you remember when we were graphing rational functions and we were looking for the horizontal asymptote? We were looking at the degrees of the numerator and the denominator. Look at try 1. When the degree of the numerator, which is 1 in this case, is less than the degree of the denominator, the horizontal asymptote was y equals 0. And look at that. Our limit as x approaches infinity is 0. When the degrees were the same in the numerator and the denominator, we took the leading coefficient, and our horizontal asymptote here would be y equals negative 2/3. And lo and behold, the limit as x approaches infinity is negative 2/3. And when the numerator's degree was larger than the denominator's degree, there was no horizontal asymptote. And look at that, there is no limit as x approaches infinity. So we can always make the connection with the horizontal asymptotes. And understanding that will simplify our process. In fact, you wouldn't necessarily have to show all of this work. You could look at the degrees and understand what the horizontal asymptote value would be, because that will be your limit. And it makes sense because graphically, when we're going, it's talking about end behavior. As x approaches infinity, we're talking about the far right end of our graph. As x approaches negative infinity, we'd be talking about the far left end. And the ends of a rational function will always be trying to approach the horizontal asymptote. So that's a good note to have. We can go back to example 2 and verify that that indeed is true. Example 2 is this ugly looking fraction, rational function, but I see that the degrees are identical, so I can just make the connection that, hey, 2/5 should be my limit, and it was, or it is. All right. So that's how you can do that. And let's look at infinite sequences and take the limits of infinite sequences as n gets very large. Here's example 3, 1/2, 1/4, 1/8, 1/16, 1/32, dot, 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 dot. Somebody's already written the rule for us, 1 over 2 to the n, 1 over the powers of 2. And I'm interested to know what is the limit as n approaches infinity of that 1 over 2 to the n rule. Well, the variable is only in the denominator. This time it's an exponent, but it doesn't matter. The variable is only in the denominator, which means the denominator will be getting very large. And if the denominator gets very large and the numerator does nothing, well, then this limit should be equal to 0. We've already talked about that. And because this limit exists, we will call this a convergent sequence. A sequence will either be convergent or divergent. Convergent, the limit exists. Divergent, of course, then, the limit does not exist. So because the limit of this sequence, or at least this rule for the sequence, existed, then it is a convergent sequence. So given that and the techniques we've already learned today, why don't you do try 4? Here is a new sequence. I'd like for you to tell me if this sequence is going to be convergent or divergent. Why don't you pause the video and try to prove one way or the other. Thanks for pausing. So if you haven't gotten the answer here yet, whether it's convergent or divergent, let me get you started. Ultimately, we are looking for this limit, the limit as n approaches infinity of our rule that has been given. So I'm interested to know if that limit exists or does not exist. Pause and try some more. So thanks for trying that. Here's our final answer. We are looking for this limit. Now you could go and show the work and divide all 4 of these pieces by our biggest power, which in this case would be n, and simplify all the little pieces and then take the limit of each of them. Or you could just make the connection that because the numerator's degree and denominator's degree are the same, you can simply take the leading coefficient, which is 2 over 1, and that the limit would then be 2 over 1, or just 2. Because the limit exists, it is a convergent sequence. And these numbers are, if they continue forever, are trying to become the value of 2. Remember, very large numbers, adding 1 is not going to do much. Adding 4 is not going to do much. So ultimately, get rid of this stuff. 2n divided by 1n, regardless of what the number is, would be 2. So let's look at our final example. Here's example 4. Now this might just look like a bunch of, work to do. This will have meaning over the next couple sections in this last topic. But right now it's simply some algebra that we'll have to deal with and then some pre-calc for our limit. To find this limit though, we must first rewrite the expression into its standard rational form. Everything here is like in factored form, and we need to undo all of that so we can see individual pieces. This process really only works when you have individual pieces, so our rational function has to be in standard form. So I'm going to need to FOIL all this together, multiply all the numerator, and multiply the denominator, and then we'll see what we've got. So the limit as n approaches infinity. Of course, we're not going to do anything with that yet. The denominator is not too bad. 6 times n cubed is just 6n cubed, so I'll go ahead and do that. I'm going to take the 8 and the n and multiply them together right now, and then I'm going to take these two binomials, the n plus 1 and the 2n plus 1, and I'm going to multiply those together by my FOIL method. The first terms give me 2n squared. The outer terms give me 1n. The inner terms give me 2n. 1n plus 2n, of course, makes 3n. And my last terms give me 1 times 1, which is 1. Okay. One more step should be enough. The limit as n approaches infinity. I've got my 6n cubed in the denominator. I've got 8n times 2. I'm just distributing at this point. 8n times 2n squared is 16n cubed. 8n times 3n is 24n squared, and 8n times 1 is 8n. All right, so now I've got my rational function in standard form, so all the pieces I can see, and now I need to find this limit as n approaches infinity. Now understand that this whole topic, n is approaching infinity, or x is approaching infinity. Our variable is approaching infinity. It's not approaching a 1 or a -7 or something from the right side or the left side or whatever. It's not a number, it's a concept. You have to take note of that. And I'm looking at this rational function, and I see, hey, look at that. The degrees are the same. Because the degrees are the same, I know that this limit is going to be the leading coefficients. 16 and 6. this limit is 16/6. Now obviously that can reduce, and we'll do that. It's 8/3. And that is our ultimate answer for this limit. If you want to use the method and divide each of these 4 pieces by our highest power n cubed and do what I taught you in the first couple examples, that's fine. But once you make the connection with the horizontal asymptote idea, then it makes it a whole lot easier to get your numbers faster so that we can use them. And I will end this lesson with try 5. Each of these converges to 0. I want to know, of these 5, which one will converge the fastest. So if all 5 of these are going to eventually get to 0, which one, well, okay, they're not going to get to 0, they're trying to be, but let's say that they all get there, which one would actually get there the fastest? I'll look for your answer when I check your notes in next time's class. Thanks for watching this tutorial. Go back and watch whatever you need to do, and we'll practice this in class. Thank you. See ya.